Okay, welcome back everyone to this video. So in this chapter, in today's video, we're gonna be covering chapter 2.5, which is the Euler-Cauchy equations. Um, as you can see, these two equations they do not have a constant coefficients. You can see for this case, some of the coefficients they're actually functions that we showed you before. And to solve this kind of equations, we're gonna use the Euler-Cauchy method. It's pretty similar to the things we have been doing before in the homogeneous second order ODEs. You can see this is still a second order. This is still a homogeneous equation. We still do a characteristic equation, but instead of using lambdas, and because this one has functions instead of constant coefficients, we're gonna be using a similar approach, but that's going to give us a bit of different results. So you can see our characteristic equation, instead of using lambdas, uses m's. We have m squared plus parentheses a minus 1, where a is that coefficient there, times m plus b. So it's pretty similar to the other characteristic equation. This is a separate method to not confuse them. So to solve this, once again, we solve for the roots, and depending on the roots, we get three cases. Case 1, you can see instead of e to the x, we have x times to the power of the roots. For the double root case, instead of multiplying times x, we multiply times ln of x. And in the complex root, once again, instead of the exponential, we have x to the real part. And instead of here just being omega times x, we have ln of x. So it's a pretty similar method. We solved them just pretty similar like before. So let's see a few examples, and hopefully you guys will get to see how these ones are solved. Okay, so we have this example here. We have x squared times y double prime minus 7x y prime plus 16y equals to 0. So the first thing that we need to do is we need to identify our a and b. So for this case, a will be equal to -7. And we have here then that b, it will be equal to 16, being these two coefficients. So based on that, we need to write our characteristic equation, which should be on the form of m squared plus a minus 1 times m plus b equals to 0. So by following this, we're going to get that our equation will then be m squared plus, in this case, will be -7 minus 1 times m plus 16 equals to 0. So solving from here, we're going to get our equation to be m squared minus 8m plus 16 equals to 0. So let's solve for the roots. So solving for the roots, we're going to get that we can factor this one out. So for this one, we have m minus 4 and m minus 4. So we'll get here then that m1 is going to equal to m2, which if we solve for this, it's equal to 4. So we get a case number 2, right? Double root. So basically we did all of this for solving the roots. And then now, depending on the case, we write our solution. So for a double root, the solution should be in the form of c1 plus c2 times ln of x, and all of that times x to the m. So in this case, our general solution for this problem will be in the form of y is equals to c1 plus c2 times ln of x times x to the 4th, because that was our m. So you can see it's pretty simple, pretty straightforward. It's pretty similar to the other problems that we have done. So there's nothing new about this that you don't know how to solve. You just use the different set of equations to solve this one. Okay, so let's solve this other example. So we have x squared times y double prime minus x y prime plus 2y equals to 0. So once again, first things we need to do is identify A and B. So for this one, we have that A is equal to -1 and B it's equal to 2. So from that, we can write our characteristic equation, which will be m squared plus A, which is -1 minus 1 times m plus B, which in this case is 2, equals to 0. And from here, we get our equation then of m squared minus 2m plus 2 equals to 0. So we need to solve for the roots. This equation we cannot factor out. We need to use quadratic equation. So let's solve for this one. So this will be m is equal to minus -2 plus or minus square root of -2 squared minus 4 times a, which is 1, times c, which is 2. All of that over 2 times 1. So rearranging all of this, we'll get then 2 plus or minus square root of 4 minus 8 over 2. So that equals to 2 plus or minus square root of -4 over 2, which we then get 2 plus minus 2i over 2, and then we get here then that m 1 and 2 is equals to 1 plus or minus I. Those are the roots for our system. And because they're complex, we get a case number 3. In the Cauchy-Euler, the case number 3 will give us a solution in the form of x to the real part times a cosine of omega times ln of x plus b times sine of omega times ln of x. So with that in mind, we can write our general solution, which will be of the form y equals to x to the real part, which in this case is just 1, times a cosine of omega is also just 1, so we just have ln of x, plus b sine of ln of x. And this is the general solution for this Euler-Cauchy equation. So you can see it's pretty straightforward. It's nothing difficult at all. You just use a different set of cases that has a different form, but the process of solving it is pretty much the same as we have done before. So that's it for this video. Hope that it was helpful. And as always, I'll see you on the next one. Good luck.